Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 2nd, 2026, just 2 days ago. It demonstrates that large language models reason with a myopic or nearsighted horizon rather than a global plan. And using this insight, the authors achieve a 16% reduction in generation costs without hurting performance. The paper is titled, No Global Plan in Chain of Thought, Uncover the Latent Planning Horizon of LLMs. And as we'll see later, the implications for understanding model uncertainty are quite significant. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, the 8 billion parameter weights are available. The page also provides a system prompt example using think tags to guide the model during reasoning. To visualize this myopic behavior, Figure 2 tracks how well the model's internal state predicts the final answer as it generates the chain of thought. On the left, in the parity task, the model must count occurrences of a specific digit. Notice how the probing accuracy hovers near 50%, essentially a random guess, for almost the entire sequence. It only spikes to 100% at the vertical dashed line, which is the exact moment the model finishes counting. The right panel shows the same phenomenon for a graph cycle task, where the model traces the path step by step and has no idea if a cycle exists until it actually encounters the repeated node at the very end. So Table 1 puts hard numbers on that observation for the parity task. The columns here track the probability of the correct answer from 4 steps back up to position 0, where the counting finishes. Look at the values for positions -4 through -2. For both models, the probability stays stuck at 0.5, essentially a coin toss. Then, at position -1, it suddenly leaps to over 90%, confirming the model lacks foresight until the very last second. Figure 1 switches focus to the very start of the reasoning process. Here, we see probing accuracy for the first 5 tokens, shown on the x-axis, across the model's layers on the y-axis. On the far left, the parity heat map is completely dark, with values stuck at 0.5. This confirms that for strict reasoning tasks, the model has zero foresight early on. In contrast, the MMLU panel shows bright orange regions in the middle layers. This implies that for semantic questions, the model often senses a gist of the answer immediately, even before the chain of thought begins. Well, Figure 5 shifts the focus from the start of reasoning to the planning horizon itself. This chart plots the top 5 accuracy for predicting future tokens, with the x-axis extending up to 8 positions ahead. Notice the 2 distinct behaviors here. For rigid algorithmic tasks like parity and cycle at the top, the lines stay flat and high, meaning the model knows exactly what comes next. But for everything else, including math and general knowledge datasets shown in the steep downward curves, accuracy crashes immediately. This suggests that for complex reasoning, the model effectively invents its path 1 or 2 tokens at a time. Alright. Figure 4 tests whether those early signals are actually reliable substitutes for full reasoning. Across these 6 datasets, the blue bar shows accuracy with chain of thought, while the orange bar is the model answering directly without it. The green bar tracks the probing accuracy, our ability to predict the answer solely from the initial hidden states. On the far left for math, notice that the green bar is barely visible above the red random baseline, confirming that logic tasks have no early plan. In contrast, for semantic tasks like CSQA and MMLU in the middle, the green bar is much higher, showing the model does have an early hunch. Crucially though, the orange bar consistently beats the green one, which means simply asking for a direct answer is more accurate than relying on these vague internal states. Since the model relies on local transitions rather than a global plan, the authors propose a wooden barrel principle, the idea that the uncertainty of a reasoning chain is determined by its most critical steps, not the average token. Table 2 validates this hypothesis by comparing standard uncertainty metrics, like perplexity, against the proposed Tele-Lens method. In the top section, the standard baselines achieve an average calibration score of only about 0.60. However, looking at the Tele-Lens top 5 row below, the score jumps to 0.69. This 9% improvement confirms that monitoring just a few pivotal moments yields a much cleaner signal of confidence than analyzing the entire sequence. So, wrapping up, the core takeaway is that large language models reason incrementally without a hidden global plan. This insight allows us to detect high confidence early and bypass the reasoning chain for easier tasks, effectively cutting generation costs by over 16%. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.